Welcome to the webinar on Basic PET Physics and Instrumentation, Part 2. This webinar is brought to you by the European School of Nuclear Medicine in close collaboration with the International Atomic Energy Agency. In this webinar, I will address the factors affecting noise in a PET image, starting from the concept of system sensitivity. Then, the time coincidence acquisition concept will be introduced. I will also analyze other sources of noise in a PET image, introducing the definition of true, scatter, and random coincidences, and the related noise equivalent count rate figure of merit. The concept of time-of-flight PET will be introduced. A particular attention will be dedicated to the attenuation correction problem and how it can be solved using an hybrid PET-CT system. And finally, a briefer review of commercially available PET-CT systems is presented. The estimation of the spatial resolution formula, described in Part 1 of this webinar, is defined assuming infinite statistics. It means that it does not include effects from noise. Noise characteristics have an important implication for quantification and detection performance in PET imaging, especially in high-resolution scanners. A first factor affecting noise in an image is the detection efficiency. Detection efficiency refers to the efficiency with which a radiation measuring instrument converts emissions from the radiation source into useful signals from the detector. Maximum detection efficiency is desirable to obtain the maximum information with minimum statistical noise and with a minimum amount of radioactivity, that means dose reduction. The detection efficiency D of a radiation counting system can be defined as D equal to R over A, where R is the counting rate and A is the source activity. The detection efficiency D is affected by several factors that can be written as a product of individual contributions. In the displayed formula, G is the geometrical efficiency, mainly given by the solid angle coverage of the PET ring. Epsilon is the intrinsic detection efficiency, obtained as the product of the intrinsic efficiency for 511 kV gamma rays of the two detectors involved in the coincidence. Small f is the electronic recording efficiency, and capital F is a factor that takes into account of the absorption and scattering in the object. The maximum D is desirable to obtain minimum noise. However, it is difficult to maximize all factors. For example, the geometrical efficiency G can be increased by reducing the scanner diameter and or increasing the axial extension. However, the minimum scanner diameter is limited by the parallax effect that worsens as scanner radius is reduced. In turn, axial extension is limited, for example, by the cost of the building material. And on the other hand, epsilon can be increased by using thicker scintillating crystals. But, once again, spatial resolution would be degraded by the increased parallax effect. In Part 1 of this webinar, we have seen how it is possible to detect and measure the position of the interaction of gamma rays. The problem is that to recognize a pair of gamma rays as being generated by the same annihilation process. For this purpose, the information on the time of arrival of a gamma ray into the detector can be used. The two gamma rays are simultaneously generated, And then, apart from some delay that may occur due to a difference in distance from the annihilation point to the two detectors, they are simultaneously detected. The selection of the annihilation gamma-ray pair using the arrival time information is called detection in time coincidence, or, in brief, coincidence detection. For this reason, it is important to be able to determine when a photon has struck a detector. In this way, the time of all detected events can be compared to determine which ones arrived closely enough in time to be identified as an annihilation pair. The ability of a pair of detectors to determine the time difference in arrival of the annihilation photons is known as the timing resolution, or tau, and is typically of the order of few nanoseconds. The maximum difference in time for a pair of detected gamma rays to be identified as a coincidence event is called time window. In order to avoid missing coincidence event, the time window should be at least 2 times the time resolution, or tau. Typically, for a BGL-based PET system, tau is approximately 5-6 nanoseconds full-width Fmax, while it is reduced using lutetium-based scintillators down to 2-3 nanoseconds. In addition, it must be considered that the minimum time window must be at least larger than the maximum delay that may occur due to the finite traveling speed. For example, for a typical clinical PET size, the maximum traveling distance is 70 centimeters. That corresponds to 2.3 nanoseconds of maximum time delay. A typical timing window that is used in PET scanners is typically between 4 and 20 nanoseconds. Along the timing branch, the PMT signal is preamplified with a fast preamplifier, thus to preserve the time information, and fed into a discriminator that produces a digital signal when a gamma ray is detected. In order to improve the time resolution of the discriminator, a constant fraction discriminator is usually implemented, thus minimizing the uncertainty on the measure of the arrival time due to the pulse age variations. The width of the digital signal generated by the constant fraction discriminator is set to be equal to the time window tau. The timing pulses are amplified and fed into a coincidence circuitry. In this simplified example, the coincidence circuitry can be a logic AND between the two logic signals that generates a coincidence signals when the two signals have a certain overlap. In this way, a coincidence is accepted when the time difference in the gamma ray arrival is within plus or minus tau. Hence, the effective time coincidence window is actually 2 tau. Along the other branch, signals from the PMTs, 4 in the case of a block detector, are digitized only if enabled by the coincidence signal. The extension of this concept to a multiple detector system can be obtained by implementing a more complex coincidence circuitry that is able to detect the pair of blocks where the coincidence occurred, thus providing a trigger signal to enable the data acquisition for the involved blocks only. To increase system sensitivity and axial field of view, a PET features various rings of detectors. In this picture, you can see the axial section of a PET system. Multi-ring PET systems are classified into two categories, 2D and 3D scanners. In 2D, detectors of a ring are in coincidence with the same ring or with detectors lying in the neighboring rings. For example, block 4A in the picture is in coincidence with 3B, 4B and 5B only. The picture only shows all the acceptable allo Rs involving detectors 4A, 5A, 4B and 5B. The allo R indicated by a dashed line is rejected by the 2D mode coincidence system. In this way, data coming from a single slice of object or patient are recorded by 1-2 rings only. This simplification makes image reconstruction process easier. In addition, in order to limit the number of single events reaching a single detector, each ring is physically separated from the adjacent one with a septum made of IZ material. For example, the dotted allo R is blocked by the septum between block 2B and 3B. On the other hand, 3D PET scanners are also able to record inter-ring coincidences. In the picture to the right, the 3D mode is shown. All possible allo R are accepted. For example, the block 4A is allowed to record coincidence with all rings. The picture shows all the acceptable allo R involving again detectors 4A, 5A, 4B and 5B. Only with the advent of more advanced reconstruction algorithms and more powerful hardware resources, the management of this 3D data has become possible. In addition to statistical noise due to the counting rate limitations of a PET system, there are several sources of noise that are, similarly to the spatial resolution limitations, caused by both the physics of the gamma-ray interaction with matter and the adopted technology. Let me clarify here that the term noise in PET is often inappropriately used to describe the fluctuations in space in the measurement of a uniform activity. A more appropriate definition is the image roughness, that is usually measured in terms of the standard deviation of the measured value. Apart from the already discussed statistical limitations, uniformity is also limited by the presence of linear responses not appropriately recorded. A recorded allo R is meaningful only when generated by a true count. A true count is a coincidence event where the gamma-ray pair is generated by a single annihilation event, and both gamma rays are detected without experiencing any other interaction along their path. In fact, only under these conditions the allo R passes by, or more correctly, the tube of response contains the annihilation point. Hence, not all the allo Rs generated by a coincidence detection of two gamma rays give true counts. The figure in the slide shows three possible types of events that can be recorded by a PET as a coincidence. The annihilation occurring in location 1 corresponds to a true count, usually indicated by the letter T, between detectors A and B. In the event originating from position 2, at least one of the two gamma rays experiences a scattering along its path. The line of response generated in this way, recorded by detectors C and D in this case, does not pass through the annihilation point. Such type of event is called scattered, or S count. Gamma-ray emissions from points 3 and 4 occurs simultaneously. The two gamma rays, although detected in time coincidence by E and F detectors, are not generated by the same annihilation. They are accidentally detected in coincidence, and this type of event is usually called accidental or random events, indicated by letter R. Also in this case, the generated halo R is not correlated to any annihilation point. The sum of true, scatter, and random events are called prompt counts, and indicated with letter P, where only true counts contain useful information for the image reconstruction. Another possible type of event is the so-called multiple counts, where more than two single events are recorded within the coincidence time window. This event generates an ambiguity on deciding which is the gamma-ray pair actually generated in a single annihilation, and thus this type of multiple event must be discarded. Note that the definition of true, random, scatter, and multiple counts assume perfect detectors. The measured true and scattered count rates vary linearly with the activity present in the field of view. On the other hand, the ratio between T and S can be usually considered constant. An important figure indicating the relative weight of the effect of scattered events onto the reconstructed image is the scatter fraction, or SF, that is defined as the ratio between the scattered count rate and the total count rate. This is true assuming that the scatter fraction is measured only when the random count rate is negligible. In this case, the total count rate is simply the sum of the scattered plus the true count rates. Scattered counts generate a low spatial frequency background that reduces the contrast in the reconstructed image. The spatial distribution of the intensity of the background generated by scattered counts depends by the activity distribution and the shape and size of the patient. Now, let's have a look on how is it possible to control the scatter component. That means minimizing the scatter fraction. When a photon interacts in the object, it also loses a fraction of its energy. In general, for a given gamma ray with energy E gamma, the relation between the scattering angle θ and the residual energy E gamma prime is given by the Compton formula, as displayed in this picture. At 511 keV, the formula can be simplified as shown. In addition, not all scattering angles have the same probability to occur. This figure shows a plot of the scattering probability versus the scattering angle. As one can see, smaller scattering angles have a higher probability to occur. Combining the two previous plots, we can obtain a spectrum of the residual energy of a 511 keV photon after a single scatter interaction. Thus, the scattered events can be discriminated by measuring the energy, that should be always less than 511 keV. Now, let's analyze what happens in the real case. Let's suppose all true counts release all the energy in the scintillator through a single photoelectric or multiple interactions. This is a simplification, because we know that after a first interaction in the scintillator, the photon could also escape before releasing all its energy. Under this assumption, we can obtain the full energy peak displayed in red in the picture, corresponding to a true count. When a photon suffers from a scattering interaction in the object, It contributes to the scatter component of the energy spectrum, displayed in green in the figure. Smaller energies correspond to a larger scattering angle, while a higher energy to a smaller angular deviation. A way to reject scatter events is to select the full energy peak only with an energy window. Obviously, increasing the width of the energy window increases the fraction of scattered counts, and the included scatter counts suffer from a larger and larger scatter angle, thus largely degrading the image. However, we cannot exactly determine the energy released in the scintillator. The ability of the detector to measure the energy of the photon is known as the energy resolution. It must be considered that typical values for the energy resolution of lutetium-based scintillators read out by photomultiplier tubes is about 15 to 20%. Here, it is evident how the energy resolution of the detector is important in PET. In fact, the better the energy resolution is, the narrower the energy window can be, and a smaller fraction of scattered events are then included. While scattered events typically generate a structured background, random events generate a more uniform background. Nevertheless, their importance becomes significant as the activity and then the single count rate increases. In fact, to obtain quantitative data in PET, it is necessary to estimate the rate of random coincidences in the measured data in each line of response. The random count rate can be expressed as Rij equal to Ci multiplied by Cj multiplied by 2 tau, where Ci and Cj are the singles count rate on detector I and J, respectively, and tau is the coincidence time window. Hence, Rij is proportional to the square of the activity in the field of view. It is clear that a narrow time window is then necessary to reduce random counts. Apart from limiting the occurrence of random counts, methods for their correction in the reconstructed image are also available. This process is called random correction. It is based on a statistical estimation of the random counts distribution that may be either subtracted from prompt events online or stored as a separate histogram for later processing. The estimation of the random count rate can be indirect or direct. In the first case, the random count rate formula previously shown is used to derive Rij from the single count rate recorded in each detector. This method is in principle precise, but may be not very accurate for the systematic error due to the a priori estimation of tau. To directly derive the random count rate, the so-called delayed window technique can be used instead. In this case, an additional coincidence processor is used. The logic pulse from one detector is delayed in such a way that it has no more correlation with the other photon of the annihilation pair. When a coincidence between a delayed pulse from detector I and a prompt pulse from detector J is detected, a counter R delayed Ij is increased by 1. At the end of the acquisition, R delayed Ij can be considered a good estimation of Rij, i.e., the number of random counts in the lore Ij. The advantage is a more accurate estimation of the random counts, even if it is characterized by a noisier distribution. The noise equivalent count rate, or NECR, is the figure of merit that quantifies the amount of background and statistical noise characteristic for a given PET scanner, thus evaluating the effect of the presence of scattered and random counts. The formulation of NECR is as follows. The noise equivalent count rate is equal to the square of the true count rate divided by the total count rate, where the total count rate is the sum of true, random, and scattered count rates, and where k is a factor that takes into account of the method used for estimating random counts. Usually, k equal to 2 when the delayed window technique is used, while k equal to 1 for noiseless random counts estimations. In this slide, you can see an example of true, scatter, random, and noise equivalent count rate curves as a function of the activity concentration obtained with a NEMA NU2 procedure on a real system. Noise equivalent count rate data are produced for both extreme cases of k equal to 1 and k equal to 2. As one can observe, the random count rate increases quadratically as the activity concentration increases. The NEC curve shows its typical behavior, with a peak of a given activity concentration. For example, here the peak is at around 20 kBer per cubic centimeter. The peak of the NEC curve and the activity at which it has been obtained represent a critical figure of merit for a PET system, because it indicates the maximum amount of activity that can be injected into a patient to obtain the maximum fraction of useful information. Another important source of noise and bias in a PET image is the intrinsic variation of the relative efficiency of the different lines of response. The procedure in which the halo-R's efficiency are equalized is called normalization procedure. This is usually performed with a blank scan with a rotating germanium-68 source. A good normalization procedure reflects in a well-uniform image when scanning a uniform cylinder phantom. The verification of the correctness of the normalization procedure is part of the daily quality control for a PET system. The same phantom acquisition can be also used for the quantitative calibration of a PET system. That means the appropriate conversion from counts to megabecquerel per milliliter in a PET image. That is possible when the cylinder phantom is filled with a known activity concentration. The procedure for measuring the performance of a PET system are described in the NEMA NU1 and NU2 documents. The main procedures include the measurement of the spatial resolution obtained with a scan of a point source for 3D PET systems, and of the sensitivity that should be measured with the accumulated sleeve technique. I'm not entering into the details of these measurements. This slide just shows the procedure applied on a real PET system. To the left, the figure shows how the system sensitivity can be extrapolated at zero attenuation from the measurements obtained with the accumulated sleeve technique. To the right, the results of the sensitivity along the axial direction is displayed, showing the typical triangular behavior of the 3D mode PET sensitivity moving along the axial axis. A way to measure the scatter fraction is also described in the same procedure documents. This is usually performed using a solid whole-body phantom with a hot tube insert. Image quality is evaluated using a dedicated torso-like phantom filled with a uniform activity concentration that includes hot and cold spherical inserts. The hot rod inserts are used to evaluate the partial volume effects. Partial volume effects, or PVEs, usually incorporate both aspects of poor spatial resolution, including partial volume and spillover spill-in effects. The spillover ratio is the fraction of activity that falls outside a region of interest equal in size to the real object. As you can see for this mathematical phantom example, as the spatial resolution value increases with respect to the object size, the spillover ratio increases, already exceeding 50% when the full width at half max equals the object size. In turn, the recovery coefficient, RC, is the ratio between the measured and true activity in an object of a given size. In this mathematical example, a PET with a spatial resolution of 4.7 mm full width at half max is assumed. As the detail size is reduced, the RC value decreases. The knowledge of the RC values is then critical to evaluate the performance of a PET system, but also they must be taken into account when quantitative measurements, such as SUVs, have to be performed, especially small lesions. In this view, it could be also important to evaluate how the contrast is changed as the detail size become comparable with the spatial resolution. For example, still assuming a spatial resolution of 4.7 mm, as the object size is smaller than 4 mm, this measured contrast is less than 30% of the actual value. Now, let's introduce the time-of-flight PET concept. As previously mentioned, the image reconstruction in PET is based on the linear response determined by the two elements that detect the two gamma rays in time coincidence. The positron annihilation point is assigned to an equal probability along the chord, that is the intersection of the LOR with the field of view, as in the red line in the picture. In principle, from the difference of arrival time of the two photons onto the opposing elements, it would be possible to determine the exact position of the annihilation point. The difference in arrival time of the two photons, emitted from point C to detector A and B respectively, is then given by delta t equal to dA minus dB divided by the speed of light c, where dA and dB are the distances from the annihilation point to the corresponding detector for photon A and B respectively. Or delta t can be equal to 2 times delta s divided by the speed of light c, where delta s is the displacement of the annihilation point from the center, as shown in the picture. Inverting the previous equation delta s can be estimated as delta s equal to c times delta t divided by 2. Hence, if one measures delta t with an infinite precision, one obtains the exact difference delta s and the values dA and dB, thus exactly locating the positron annihilation in 3 dimensions. However, because of the finite precision on delta t, defined as sigma t, the associated uncertainty on delta s is sigma s equal to c times sigma t divided by 2. This technique is called time-of-flight PET or TOF PET because it makes use of the difference in the time of arrivals of the 2 photons onto the opposing detector. This technique is based on a very high time resolution. For example, with sigma t equal to 400 picoseconds, full width at half max, it would be possible to measure the position of the annihilation point with a precision of 6 centimeters. Hence, time-of-flight measurements do not improve directly the spatial resolution of a PET system, which is still of the order of 4 mm in clinical PET, but dramatically contributes to increase the signal-to-noise ratio of the image. Till now, in the description of the PET technique, we have neglected the effect of the attenuation of the emitted gamma rays in the interaction on the patient itself. At 511 kV, the attenuation coefficient μ in soft tissues is about 0.096 cm to the -1, while in bone is about 0.17 cm to the -1. For this reason, there is a relatively high probability for a gamma ray to interact in patient tissues before reaching the surrounding PET detectors, mainly via Compton scattering or photoelectric absorption. Formally, the line integral introduced in part 1 of this webinar should be modified as a consequence of the gamma ray attenuation along a linear response. Hence, the counts along a linear response L and gamma gamma, for example from detector 1 to 2 as in the picture, should be proportional to the integral along the line L, that is of the quantity ρ multiplied by P1 and P2, where P1 and P2 are the probabilities for the 2 gamma rays to reach detectors 1 and 2 respectively, that in turn are expressed by a simple exponential attenuation formula, whose attenuation coefficients is obtained by integrating all μ values along the lines L and L1 and L2 respectively, that connects the emission point to the 2 detection points. Thus, the probability P for both gamma rays to reach the corresponding detectors and then contributing to a certain linear response is the product of P1 and P2. After some simple calculation, one can note that the probability for a count to be detected does not depend by the position of the annihilation point along the linear response, but only by the line integral of the attenuation coefficient along the LOR itself. In this way, it is possible to factorize the line integral that should be used for image reconstruction and the attenuation contribution. The quantity 1 over P, usually called attenuation correction factor or ACF, it is used as a multiplicative factor to correct the emission projections before image reconstruction. To have an idea of the relative weight of the attenuation correction factor, It must be noted that mu in soft tissue is equal to 0.096 cm to the minus 1, and then with a 40 cm diameter patient, the ACF is about 50. Similarly to scatter correction, attenuation correction is a necessary step in the image reconstruction for PET. There are several ways to derive the attenuation correction factors for each line of response. The most common approach consists in a direct or indirect estimation of the attenuation correction factors through the measurement of the distribution of the attenuation coefficients mu at 511 kV in each point of the patient. A typical way to directly measure mu is the use of the so-called transmission scan method, that consists in measuring the attenuation of a gamma-ray beam along a certain lore in the presence of the object. The attenuation is measured by comparing the counts recorded along a certain line in the presence of the object, transmission scan, to those obtained without the object, called blank scan. Attenuation data along all the line of responses are collected, for example, by rotating the source around the object, thus creating a sort of transmission scan and a blank scan scintillators. The hollow R is thus defined by the coincidence between the near side and the opposite side detectors. Thanks to the coincidence collimation of the beam, a linear source, called a rod source, can be used. The ratio between the two scintillators gives the attenuation correction scintillator, containing the attenuation correction factors, to be used as a multiplication factor for the emission scintillator. The advantage of this approach stays in its relatively low technological complexity and in the accuracy of the result. However, there are several constraints: long scan times, noisy attenuation scintillators due to the low statistics, needs for replacement of the transmission source every 12 or 18 months. In addition, since a post-injection transmission scan is more desirable in the clinical settings because it increases patient comfort and scanner throughput, the transmission scan acquired after the injection of the PET tracer would suffer from contamination by 511 kV photons emitted from the patient tracer, resulting in a reduced image contrast. Before the advent of PET-CT systems, almost all clinical PET systems were featuring some sort of transmission scan technique based on radioactive sources to perform attenuation correction. Now let's analyze how the advent of PET-CT systems changes PET. Hybrid imaging can be defined as the use of information derived from images obtained with different techniques to provide the answer of a single clinical question. The power of hybrid imaging increases when the two techniques do not only provide complementary information, but they also help each other in improving the quality of the images with respect to a standalone technique. One brilliant example of hybrid imaging is the combination of PET and X-ray computed tomography. The information derived from a CT scan is then highly complementary to the PET information, since the CT provides an anatomical reference to the activity density map, RAW. In addition, tissues are well characterized in possible anatomical abnormalities as a consequence of the disease, while PET is able to provide functional or molecular information only. A PET-CT hybrid systems comprises a PET scanner and a CT scanner axially juxtaposed, and sharing the same geometrical axis. The two scans, even if separated, must perform in a well-known relative reference frame, so as to be able to fuse the two images. A further advantage of the hybrid PET-CT is the possibility to obtain attenuation coefficients from CT to be used after some corrections for the attenuation correction of PET data, thus further improving the quantification capability of PET. The correction steps include the spatial co-registration of PET and CT images, the energy scaling, and the resolution scaling obtained by smearing the CT image to the PET resolution. Thanks to the high flux of X-rays used in CT scanning, low-noise attenuation maps can be derived in a fast and accurate and precise way, but the values of attenuation coefficients are far from being accurate. In fact, the attenuation coefficients obtained at the CT energies are far from the values of those at 511 kV that should be used for PET attenuation correction. This makes energy scaling the most critical correction step in CT-based attenuation correction process. Energy scaling cannot be performed with a simple multiplicative factor. In fact, for the energies in use, the relative probability for the various interactions to occur, Compton of photoelectric interactions, varies significantly between CT energies and 511 kV for the various tissues in the human body. In particular, strong variations can be observed between bones and soft tissues. For that reason, in its simplest form, one can separate the CT image into regions corresponding to different tissues type. For example, soft tissues, lung, or bone only. Each material receives a constant mu at 511 kV. This procedure is called segmentation-based attenuation correction. Today, a more common approach is the energy scaling obtained with a linear scaling with a coefficient from minus 1000 Hounsfield unit up to a given Hounsfield unit value, for example 0, and with a different coefficient, typically lower than the previous one, above that value of Hounsfield units. In the lower range of Hounsfield units, soft tissues are included, while bone lays in the upper range of Hounsfield units. Conversion coefficients and thresholds values are usually suggested by the scanner manufacturer. Some more complex scaling are also used sometimes, but are all based on some form of linear conversion. The linear scaling approximation fails in the presence of high Z materials that cannot be approximated as a mixture of air, water, and bone. This may occur, for example, in the presence of metal implants or when CT contrast agents are used. In this example, you can see the effect of attenuation correction in a brain study. In the non-corrected image, the deepest brain regions show less activity concentration than expected, and a typical halo appears outside the head. After CT-based attenuation correction, the correct uptake ratio is recovered, as shown in the picture below. This is of particular importance, for example, in oncological study. Only when attenuation correction is performed, the correct SUV can be accurately measured. On the other hand, CT-based attenuation correction must be always used with some attention. In this example, some hot spots are visible between the lungs in the attenuation-corrected image. The reason could be the overcorrection of the attenuation due to the presence of a pacemaker that caused an artifact in the CT image. As a confirmation of this hypothesis, the non-attenuation corrected image is shown, confirming the absence of hotspots in the patient. There are also other potential problems in analyzing PET images after CT-based attenuation correction. The difference in CT and PET respiratory patterns can lead, for example, to artifacts near the dome of the liver. The use of contrast agent or implants can cause incorrect values in the PET image. In addition, truncation of CT images due to keeping arms down in the field of view to match the PET scan can cause artifacts in corresponding regions in PET image. And finally, bias in the CT image due to the beam hardening and scatter from the arms in the field of view. There are also other potential problems in analyzing PET images after CT-based attenuation correction. The difference in CT and PET respiratory patterns, for example, can lead to artifacts near the dome of the liver. The use of contrast agents or implants can cause incorrect values in PET image as well. The truncation of CT image due to keeping arms down in the field of view to match the PET scan can cause artifacts in the corresponding regions in PET. And finally, bias in the CT image can be caused due to beam hardening and scattering from the arms in the field of view. In some cases, non-attenuation corrected PET images may look better than the attenuation corrected ones. Some perceived advantages of reconstructing images without attenuation corrections are, for example, avoiding noise amplification, reducing patient scanning time, or improved contrast-noise ratios for lesions. Those perceptions are incorrect. However, there are valid reasons for reconstructing PET images without attenuation correction. For example, for checking the presence of artifacts introduced by patient motion occurring between the emission and transmission scans, or mechanical problems with the transmission scan itself, or attenuation correction artifacts for the excessive beam hardening due to the metal artifacts or truncation in the CT image. In this last part of the webinar, let me show the main feature of modern PET-CT systems. As of today, almost all PET systems use lutetium-based scintillator, with only one still using BGO, with the aim of maximizing system sensitivity. The crystal pitch ranges in these systems from 6.3 down to 4 mm. Time-of-flight capability is featured in almost all systems, but the one using BGO. PMTs still represent the preferred choice for the photodetector, but silicon photomultipliers have been recently introduced in clinical systems. As we have seen, an important figure of merit in PET is sensitivity. Sensitivity is dominated by detector material and thickness, but also by ring diameter and axial field of view extension and recording efficiency. Regarding field of view diameter, one must be also consider that only PET with a larger bore can accommodate obese patients. As of today, all the commercially available PET-CT systems have in general comparable configuration and performance parameters. It is also clear that time-of-flight imaging is generally superior to non-time-of-flight because of the improvement in the signal-to-noise ratio. However, some difference among these systems can be found in the gantry aperture and axial field of view extension, or in the CT performance or in the availability of time-of-flight capability. In the last 15 years, PET-CT changed the rules of nuclear medicine, with an impressive image quality improvement with respect to standalone PET. On the other hand, some drawbacks are still present. PET-CT is always a sequential measurement, and involuntary subject or physiological movement are possible, leading to movement artifacts. Furthermore, the additional radiation exposure due to radiation by CT cannot be neglected, and this can be critical in pediatric investigations and in repeated follow-up studies. But now the rules are changing again, with the advent of a next-generation gold standard technique, the hybrid PET-MR. Thank you for your attention.